Every time you ask, like a generative AI to write a poem, or you instantly sync a massive 4K video project to the cloud, the experience feels completely weightless.
Oh, totally. Like magic.
Right. It feels like this digital magic just happening in the ether. But the physical reality is, well, it's anything but invisible. I mean, there is no ether.
No, definitely not.
Somewhere in the world, there are massive, screamingly loud, unbelievably hot rooms filled with thousands of metal boxes just spinning up to make that magic happen. And today, we are walking straight into the engine room of your digital life. Welcome to the deep dive.
It really is an incredible operational puzzle.
Yeah.
We're going to explore how the people running these massive, constantly evolving data centers actually manage the sheer physical chaos.
Because it is chaos, right.
Oh, absolutely. How do they keep these facilities from literally melting down or from completely bankrupting the companies that build them?
Because, I mean, managing servers used to be pretty straightforward. You'd walk down a freezing cold aisle with a clipboard and manually plug in Ethernet cables.
Right, the old days.
But that era is completely dead. Today, we're diving into the reality of smart grids, incredibly dense AI superclusters, and get this, automated leak detection for server racks that are literally cooled by flowing liquid.
It's wild to think about.
It is, and we're anchoring this exploration around a 2026 solution brief from Supermicro. It's detailing their SuperCloud Composer, or SCC. It serves as a really fascinating window into this hidden world.
Yeah, and to really understand the value of a system like SEC, we first have to look at the immense pressure these modern facilities are under.
Right.
They're expected to be flawlessly efficient, yet they're dealing with layers upon layers of different hardware generations all crammed into the same building.
Because they don't just throw the old stuff away.
Exactly. You might have, say, 5-year-old traditional storage drives sitting in a rack right next to the absolute newest bleeding-edge AI accelerator.
Okay, let's unpack this. If you have all that different equipment, the legacy way of managing it must be an absolute nightmare.
It's a massive headache, yeah.
I keep picturing the early days of trying to set up a smart home. Imagine if your living room had, like, a smart light bulb, a thermostat, a security camera, and a wireless speaker.
Okay, I see where you're going.
But every single device required a totally different app on your phone. And maybe a different physical remote control on your coffee table just to turn them on.
That sounds awful.
You'd go crazy. That is the traditional data center, isn't it?
That is a highly accurate way to visualize it, actually. Historically, infrastructure management was terribly fragmented. An IT team would have one completely isolated software tool to manage their storage arrays, another for their network switches, a different one entirely for the compute servers, and yet another dashboard just to watch the power distribution. When your management tools are siloed like that, you end up with heavily underutilized resources.
Because you can't see the big picture.
Right. You simply cannot scale operations efficiently when human beings have to manually cross-reference 4 different screens just to deploy a new application.
So what Supermicro is pitching with the SuperCloud Composer is essentially the ultimate universal remote control.
Exactly.
They call it a single pane of glass for the entire life cycle of the data center. So that's covering day 0 planning, day 1 deployment, and day 2 ongoing operations.
And what's fascinating here is how they engineered the back end of this universal remote to handle that kind of massive scale.
Okay.
Because the interface is just the tip of the iceberg. SuperCloud Composer is actually built on a Kubernetes backend.
No, I hear Kubernetes mentioned all the time in tech circles as a container orchestration system. But what does that actually mean for the person trying to keep the servers running?
Think of it like a massive, highly automated shipping port.
Okay.
Instead of building one giant, fragile software application that runs everything, the software is broken down into tiny, independent shipping containers called microservices. So if one specific service needs an upgrade, say the tool that monitors network traffic, you just swap out that one container.
Oh, so you don't have to take the entire management system offline just to run a security update.
Exactly.
Which makes total sense, because if this is the only remote control you have for the entire building, you can never, ever turn it off.
Precisely. That architecture inherently provides high availability and horizontal scalability.
Right.
It allows the platform to manage up to 20,000 hosts without breaking a sweat. It also utilizes something called a northbound redfish API.
I wanted to ask about that because that specific API standard comes up constantly in these infrastructure discussions. Why is it so critical here?
Well, because these massive facilities don't exist in a vacuum.
Right.
The IT teams running them already use complex automated DevOps frameworks and, IT service
Oh,
management
like
tools.
ticketing systems and deployment scripts.
Yeah, exactly. The Redfish API acts as a universal standardized translator. It allows SEC to talk securely to those existing third-party systems.
Okay, so a company's overarching automation software can essentially write a script that talks to SCC, which then physically reconfigures the servers.
You got it. It allows you to treat physical infrastructure as if it were just lines of software code.
That's incredible. But, so if this universal remote can effortlessly handle traditional servers and storage drives, what happens when you introduce something that runs 10 times hotter, uses exponentially more power, and requires an entirely different network architecture?
You're talking about the AI clusters.
I am talking about the massive generative AI cluster.
Yeah, that is easily the most demanding environment in computing right now.
Because it's fundamentally different,
Oh,
right?
absolutely. Generative AI and large language model workloads require a completely different setup than traditional cloud hosting. When you load a standard website, you are generally hitting one isolated server.
Right.
But when you ask an AI to, say, generate a video, you're engaging thousands of highly specialized GPUs that all have to communicate with each other simultaneously to process that single request.
And the SuperCloud Composer has a specific AI supercluster module built just for this scenario.
It does.
It gives the operator a unified view of all these crazy components. So you have the compute trays housing the processors, the high-speed NVLink switches that let the GPUs talk to each other without traffic jams,
Crucial for AI.
and the massive power shelves feeding them juice. It even allows operators to manage these systems as flexible resource pools across a POD architecture, bypassing the need to directly log in to individual BMCs.
Which is a massive paradigm shift in administration.
I actually need a quick refresher on BMCs. That's a baseboard management controller.
Yeah.
What is its actual job?
Think of the BMC as a tiny, unkillable parasite computer living inside the main server motherboard.
A parasite computer. I love that.
It really is. Even if the main server completely crashes, catches a virus, or the operating system is corrupted, the BMC is still awake on its own dedicated standby power.
Oh, wow.
It allows an admin to remote in, diagnose the catastrophic failure, and literally resuscitate the machine from afar.
Oh.
Traditionally, an administrator would have to securely log into each server's BMC individually. SC pulls all of that control into one place.
Okay, here's where it gets really interesting. Because I'm looking at this flexible resource pool idea, and honestly, I'm getting a little anxious.
How so?
Let me puzzle this out. If I have one master interface controlling tens of millions of dollars of incredibly sensitive AI hardware, what stops a tired junior admin from accidentally hitting the wrong button and turning off a server pod that's in the middle of a 30-day LLM training run?
Oh, that's the nightmare scenario.
Right. When you centralize all that control into one shiny dashboard, don't you also centralize a massive amount of operational risk?
It is a completely valid concern.
Yeah.
A single wrong click could literally waste millions of dollars in compute time and electricity.
Yeah.
But the platform mitigates this through deeply integrated role-based access control, or RBAC,
Okay.
and that aligns with modern zero-trust security policies.
Meaning you give people different sets of keys to the kingdom based on their actual job title.
Yes, exactly. You can specify that, say, a certain thermal analyst only has read-only access to view temperature metrics, while a senior engineer might have permission to update firmware, but crucially, only on a specific POD of servers dedicated to testing, not the live production clusters.
Okay, I get the intentional security side of it. Limiting access stops bad actors or people poking around where they shouldn't be.
Right.
But what about just honest mistakes? Not malicious, just a really bad configuration change because an engineer didn't realize how the physical systems were connected.
That is where the platform's topology module becomes critical.
The topology module.
Yes, it provides an interactive visual mapping of the networks. It displays connected nodes and links in real time.
Sort of like looking at a live subway map of your entire data center.
That is a perfect way to visualize it.
Yeah.
Imagine a sprawling city subway map.
Right.
If you need to shut down one major station for maintenance, you can't just do it blindly. You need to know exactly which train lines route through that station.
Because if you close it, you force all those trains to reroute and cause a catastrophic pileup at the next junction.
Exactly. The topology hop view highlights those interconnected switches and systems. Before an operator pushes an update or changes a network path, they instantly see the dependency chain.
Oh, that's smart.
They can visually spot congestion points, drastically reducing the chance of taking down a critical AI cluster just because they didn't realize it relied on one specific obscure network switch.
So the software is acting as a visual guardrail to prevent human error.
Yes.
But these AI superclusters bring us to a much more physical, visceral problem. Software guardrails are great, but the sheer computing power required for generative AI draws an immense amount of electricity.
Unbelievable amounts.
And
Yeah.
electricity inevitably turns into heat. So software management eventually has to collide with physical reality.
The inescapable physics of computing.
Yeah.
You cannot negotiate with thermodynamics.
I really can't.
This is why the platform dedicates an entire cooling infrastructure module and a power grid console module to tackle this. It isn't some secondary feature. Managing the physics is core to the survival of the hardware.
Let's look at the cooling first, because the hardware involved here sounds like absolute science fiction. I mean, air cooling just isn't enough anymore, is it?
Not for these AI chips, no.
Blowing air over these incredibly dense modern GPUs is like trying to put out a bonfire by blowing on it.
Yeah.
It just doesn't move the heat fast enough.
That's a great image, yeah. It just doesn't work.
So the software manages liquid cooling components. We are talking about literal fluid running through the racks of electronics.
Yes, actual liquid.
Direct-to-chip cold plates that sit right on the silicon. In-row coolant distribution units acting like mechanical hearts pumping the fluid, and rear door heat exchangers acting as massive radiators.
And when you run coolant directly over the microchips, you introduce a completely new, terrifying failure mode.
Mixing water and multi-million-dollar electronics.
Exactly. It's inherently risky.
Which brings us to the feature that absolutely blew my mind. The platform has automated leak detection and continuous thermal anomaly detection. If a single drop of liquid is detected where it shouldn't be, policy-driven power enforcement automatically isolates or shuts down the equipment to prevent a catastrophic short circuit.
It constantly correlates sensor events. A sudden pressure drop in a coolant line, a mechanical valve failure, or an abnormal moisture reading instantly triggers hard-coded policy rules.
It's like the data center's biological reflex arc.
I like that.
If you accidentally touch a hot stove, your body instantly pulls your hand away before your brain even fully processes the pain.
Yes.
The software senses a leak and cuts the power to that specific rack before the hardware is destroyed, all without a human needing to be awake, let alone clicking a mouse.
The reflex arc of a data center. That captures the speed and necessity of it perfectly. And if we connect this physical management to the bigger picture, this system isn't just about preventing catastrophic floods.
How?
No, it is fundamentally about economics and global sustainability.
How so? Because of the sheer amount of power these buildings draw.
Unimaginable amounts of power. We are talking about single facilities drawing as much electricity as a small city.
Wow.
The power grid console tracks real-time electrical telemetry. It maps every single server to its exact physical outlet on a power distribution unit.
So it knows exactly where every watt is going.
Yes, it acts as the ultimate system of record for load, loss, and efficiency. It constantly calculates PUE.
Okay, PUE being power usage effectiveness. Let's break that down, because it sounds like generic corporate jargon, but it's really the holy grail metric for these facilities, isn't it?
It absolutely is the defining metric of a data center's success.
Yeah.
PUE is the ratio of the total amount of energy used by the entire facility compared to the energy actually delivered to the computing equipment doing the math.
Okay.
An ideal, mathematically perfect PUE is 1.0, meaning every single watt entering the building goes directly into a processor.
But realistically, you have to power the lights, the physical security systems, and most importantly, the massive mechanical cooling infrastructure.
Exactly. So if your PUE is 2.0, you are spending just as much electricity running the air conditioners and liquid pumps as you are running the actual computers.
Oh, wow. You're effectively doubling your power bill just to fight the heat.
Which is financially ruinous at scale.
Yeah, I bet.
By constantly monitoring PUE, forecasting future cooling capacity based on upcoming workloads, and identifying thermal hotspots visually, the management software turns raw telemetry into actionable insights.
So it tells you if you are wasting thousands of dollars an hour just pumping chilled liquid to a rack that isn't even running a heavy workload.
Precisely. It dynamically aligns the physical cooling operations with the actual IT demand in real time. Energy is the highest ongoing operational cost of running a data center, second only to buying the hardware in the first place.
That makes sense.
You have to optimize it, or you simply can't compete in the AI space.
Okay, so we've covered the chaos of legacy hardware, The universal remote solution, navigating the complex AI clusters, and managing to not flood the data center with coolant while keeping the power bill in check.
We've covered a lot.
But let's bring this down to earth. How does a facility actually run a management system like this? What does it take to deploy it?
The deployment options are built for massive enterprise environments. You can run it on dedicated bare metal hardware or as a virtual machine appliance.
Okay.
It requires a highly secure enterprise-grade Linux environment like Rocky Linux or Ubuntu because, as we discussed, it literally holds the keys to the kingdom.
Right, you don't want that running on a vulnerable OS.
Exactly. But the truly revealing part isn't the operating system. It's the physical hardware requirement just to run the management software itself.
The remote control itself is an absolute beast.
It is. The recommended specifications just to run this dashboard include 32 or more CPU cores, 256 gigabytes or more of RAM,
Yep.
and terabytes of ultra-fast solid-state storage.
Wait, 256 gigabytes of RAM just for the remote.
Just for the remote.
That is a wildly powerful, incredibly expensive machine, and it exists solely to watch the other machines.
And that highlights the sheer scale of the infrastructure powering our daily lives. The fact that it takes a literal supercomputer just to organize the supercomputers.
That is mind-boggling.
It is ingesting and analyzing millions of data points per second from thousands of hardware sensors.
So what does this all mean for you, the listener? You don't have liquid-cooled AI servers in your living room,
Probably not, no.
but your life is entirely dependent on this invisible infrastructure. When you collaborate on a massive document with coworkers in real time without any lag, or when your Maps app instantly reroutes you around traffic using predictive AI, it is because tools like this are executing day two operations constantly in the background.
They're doing the heavy lifting.
They are monitoring temperatures, mapping network dependencies, optimizing power flows, and self-correcting errors before you ever see a loading screen on your phone.
It's an operating system for a building. That's the best way to conceptualize it.
I love that phrase.
We are no longer managing individual servers. We are managing massive, sprawling physical facilities as a single software-defined entity.
What a journey. We started with the basic premise of efficiency pressures in modern data centers, causing a desperate shift from rigid, siloed management tools to a system acting as a single pane of glass. Right. We looked at how it tames the incredible network complexity of AI superclusters, and then how it handles the brutal physical realities of power consumption and literal liquid cooling to keep everything from catching fire.
It really highlights the invisible bridge between the effortless digital actions we take every day and the immense physical infrastructure required to execute them. And, this raises an important question, something really worth pondering.
Honest.
They discussed how the software uses automated policies to instantly shut down servers if a cooling leak is detected, functioning like a biological reflex arc.
Right.
As these management platforms gather more data years of performance metrics, thermal forecasting, predictive power analysis, how long until the data center becomes completely self-healing?
Yeah.
We are looking at a very near future where AI software is entirely responsible for predicting hardware failures before they happen, physically rerouting coolant valves, and migrating workloads to keep the physical hardware of other AI systems alive.
Oh, man.
The human operators will simply be watching the dashboard while the machines completely maintain themselves.
An AI keeping another AI's physical body alive. That is a wild, slightly intimidating, but incredibly fascinating thought to end on.
It really is.
Thank you, as always, for joining us on this deep dive. Next time you stream that 4K movie or prompt an AI, take a second to picture the massive, liquid-cooled, self-monitoring engine room working silently in the background to make it happen. Keep questioning how the digital world around you is physically built. We'll see you next time.